we're off. Okay, so today we're just doing examples of vector word problems from the homework. Today is September 25th. Does that sound right?
Yeah.
Okay. And in our book it is page 517, and we're going to start with number 19. Maybe go on from there. Okay, so starting with number 19 says, find the magnitude and direction of the resultant of two forces. This one's a little hard to read. What they're finally saying is there's a 250-pound force, okay? And it's acting at an angle of 25 degrees to the horizontal. To the horizontal makes life a little bit easier. And there is a 45-pound force. Now, I'm not going to be super picky on your work, but I'd like you to try and make a 45-pound force about 1/5, mine's too big, of a 250-pound force. Okay? And then they say that this angle is at 250 degrees, which looks something like that. And it's a 45-pound force, it says? Okay.
Yeah.
Jack, what's your question?
How do you know where the drawing looks? Let's say you have one force at X angle, another force at Y angle. How do you know where to draw the two of them?
Okay, beautiful opportunity to remind us something. Vectors are totally independent of location.
Okay.
You can draw them anywhere you want as long as you keep the magnitude and the slope the same.
Oh.
Okay? I find this easiest to picture if I draw them with their tails at the origin.
Okay.
But that's a choice.
So it's fine, we just make different triangles?
Yes, well, we'll break this up into separate triangles in a second.
That's a lot easier.
Yep, okay, we'll do that. But this is what's actually going on. Now, I do have to reiterate that one thing that's really helpful to see what the vectors are doing, this is not how we're going to find our final answer, but I want to move this drawing over to here and try and duplicate it a little bit. Something like that. You can, like I just said, slide vectors around anywhere, as long as you keep the angle and length the same. So imagine that I take this vector and just decide to draw it here. So whatever I draw over here has to be parallel to and equal in length to the original one. And let's say I take this 250-pound vector and decide to draw it with its tail there. This forms a parallelogram, or it should if my drawing was a little better. And the result of these two forces acting on the same object will be what you get when you connect where both vectors started with where both vectors end. So we expect our answer to look something like that. I'm not going to go back to how parallelograms work and have you figure out the length of that diagonal and the angle of that diagonal from this. That's kind of a pain in the butt. I've done it that way before. It's annoying. But this is a good way to picture what we should expect, which is if you've got first off, if you've got 250 pounds pulling in this direction and 45 pounds pulling in this direction, what do you expect to win?
The 250 pounds.
The 250 is going to win. But is the 45 pound going to make a difference?
Yes.
Yeah. Like a small dog nipping at your heel, it's going to pull you back, it's going to drive you off course. Like when you've got that one broken wheel on the shopping cart.
Oh, yeah.
You're trying to push the shopping cart this way, and you're going to win, but that one bad wheel is going to pull you a little bit off. Okay? So that's a good way to visualize it. I think this vector makes sense that the 250-pound will mostly win, but it will be slightly shrunk and slightly pulled downward by this thing. Yes?
Is that how they do the Mars with the Voyager 1 when they shoot it off a lot of gravitational pulls and stuff?
In 3 dimensions with time and vectors that curve, yes. So,
The more complicated way.
yeah, you got x, y, z, and you've got what are called parametric equations where time is controlling where x, y, and z are, and the vectors curve. So other than that, it's exactly the same. Yes, but this is the baby steps towards that. It really is. All right, I'll stick with blue for this one. Let's look at each vector separately. Every individual vector, and we did this before we started adding them together, every individual vector can be described as a horizontal component and a vertical component combined. Now, adding vectors is kind of like walking a path, but we'll get to that in a sec. Here's my horizontal component, here's my vertical component. And they'll always form a right triangle. Horizontal and vertical always form a right angle. So the idea behind this is, and two of us demonstrated this with the desk during lunch earlier today, if one person pulls something horizontally and another person pulls it vertically, that can be the exact same thing as if some other person just pulled it at an angle. Another way to look at this is sort of like paths. You can add any vectors together and they'll add up to this first vector if you would have wound up at the same space. You can walk east, then walk north. In terms of displacement, how far you are from where you started, it's the same thing as walking northeast. I know this vector plus this vector equals this vector because if I follow this path and then this path, I wind up in the same place as if I just followed the hypotenuse. That's what vector addition means. Will you wind up where you would have anyway? If the answer is yes, then the vectors you took the long way add up to that vector. Does that make sense? Okay, yes, Jack?
So it's kind of like displacement. You just add.
It's very much like displacement in physics, yeah.
So you just add two components, and it doesn't really matter how you do it, where you go, as long as you go to the same place.
Well, you can't add them directly. You have to add them according to the geometry. You have to follow the Pythagorean theorem. So you can't just say this length plus this length.
Okay.
But if you add them in 2 dimensions, addition here meaning following this vector and then following the next vector, that's what adding these two means, and you wind up in the same place as if you just followed the diagonal vector.
How does that help?
Let's find out in a sec. Well, first, tell me what these two components are like. Don't have to give me a number, but how would I find the magnitude of this green vector, which is horizontal? It's at a 25-degree angle with the hypotenuse. What'd you do?
The cosine of 25. No, 250 cosine 25.
Excellent. Magnitude of the hypotenuse. So this green vector is 250 times the cosine of 25, because if you're looking for the adjacent side of a right triangle, it's always going to be the hypotenuse times the cosine of the angle. In that vein, who other than Jordan can tell me how to find the size of the red one? Jack?
250 sine 25.
250 sine 25 degrees. Should be consistent, use my parentheses. Okay? So, now we can't add these directly. This is horizontal, this is vertical. It's kind of like x's and y's in an algebra equation. They're not like terms. I can talk all day about how adding them means to follow the cosine and follow the sine will be in the same place as if you just followed the hypotenuse. But in the end, whatever this number is, I can't just add it to this number and get anything meaningful. Vector addition doesn't work that way. You have to take the 2 dimensions into account. Let's step away from this for a sec. Let's do the same thing for the 45-pound vector. I have this 45-pound vector going down here, right? That's a little bit small. Hopefully I'm recording in high enough definition. I'm going to go out of scale for a second here. I have this 45-pound vector. Which way is its horizontal component going, left or right?
Left.
Left. We go to roughly under there. Because this vector is going down and to the left, its horizontal component has to go to the left, and its vertical component has to go down. So what I'm doing is I'm breaking this vector down into 2 subvectors that get me to the same place. Let's see, what do we know about this vector? It's at a 250-degree angle up here from the horizontal. So who knows what this angle will be, this little one in red?
20.
How come?
Because 270 is directly down, so 270 minus 250.
Excellent. 270 would be 3/4 of the way around to directly down, as Chris put it, which I like. And we're only at 250, so we're 20 degrees away from that. All right? That's a 20-degree angle. This is a right triangle. This is 90. If that's 20, how many degrees are left to get to 180? How many? 70. Which would also be our reference angle. That's not a coincidence. That's another way to sort of find the reference angle and picture it.
Wait, what would be why would that be coincidence?
Oh, it's not a coincidence, I said.
Oh, okay.
It's a reference angle. The reference angle is with the x-axis, right? So when you draw your radius down here, if we're back on the unit circle, with this horizontal being parallel to the x-axis, you're going to get a transversal and alternate interior angles. So your reference angle will always be the same as that angle. Remember your geometry proofs and all?
Vaguely.
All right. You don't really have to, as long as you can figure out that 70 degrees. You can do it this way every time.
Okay, cool.
And it turns out you can also put 250 in your calculator and you'll be okay, but we'll get back to that. All right. How do I find this horizontal? This adjacent side of this right triangle?
Sine.
Adjacent. SOHCAHTOA.
Ha. Cosine.
We have the hypotenuse, so we want cosine. We're looking for a relationship between adjacent, which we want, and hypotenuse, which we know. Adjacent and hypotenuse, that's cosine. Okay, horizontal is always cosine. Yes, Ethan?
70 cosine 45. Oh, word.
Said it exactly backwards.
Did I?
Yeah.
45.
It's 45 cosine 70. So make sure you get it right when you punch it in the calculator. Yes, I did. We could have just done 250 in the calculator, but I want you to know why. All right? But since we didn't do 250, we have to take something else into account. Which way is this going?
Down.
No, the horizontal one's not going down.
Going right. And left.
Oh, negative, in the negative direction.
It's going left, which is in the negative direction. Okay? So with that in mind, how do I write the height?
Positive.
The vertical part.
Negative 45 sine 70.
Negative 45 sine 70. Why negative, Jack?
Because it's going down.
Excellent.
You're right. Never mind.
Yes, sir.
So you could also go by the angle 20, like 20 degrees.
We could have. Yes, we absolutely could have.
All right.
I don't want to do that because I've been saying you'll, to keep things consistent, I've been saying cosine for the horizontal and sine for the vertical, and that will switch them. So I'd rather not say that, but yes, you could. Okay,
So-
one way to look at this is if we do a bit of substitution. This still doesn't get us to our answer yet, okay? But the problem didn't say take this force and break them down into their horizontal and vertical components. The problem said figure out what happens when these two forces act on an object. And this is the part that some of you guys have been struggling to set up correctly. So here's what we're going to do. We're going to say, I'm going to write this out as if it were an addition problem. Here is 250 pounds at 25 degrees plus 45 pounds at 250 degrees, right? What does it mean to add this shape to this shape? That's kind of weird, two-dimensional shapes. In fact, I don't like that. That looks weird and confusing. You're adding something in 2 dimensions to something else in 2 dimensions. You guys are used to adding numbers, right?
Yeah.
Okay. We should remember something from geometry called the substitution property. And maybe do some substitution in other classes, solving linear systems. If 2 things are the same, you can always substitute.
Yeah.
Okay, here's the deal about vectors. Vectors are all about displacement, not distance. If this vector and this vector will make a path that gets me to the same place as this one long vector, if the horizontal vector and the vertical vector will get me to the same place as the hypotenuse, then these 2 vectors added together are the same thing as the hypotenuse. That makes, they get you to the same place, right?
Yeah.
Any set of vectors that gets you to the same place is equivalent. It's all about the displacement, not the distance, physics kids. Okay? Will I be in the same spot if I go horizontal then vertical as if I take the shortcut?
Yeah.
Yes.
Okay, then they're the same vectors. So I'm going to substitute. I'm going to change this to horizontal vector of 250 cosine 25 plus a vertical vector, which I did in red, correct? Of 250 sine 25. Can I just, for this first vector here, can I just substitute these 2?
Yeah. For that one right there.
These 2 vectors can replace
Yeah.
this 250-pound hypotenuse, right? Okay? And then for my 45-pound vector at a 250-degree angle, can I substitute these 2 vectors?
Yeah.
A horizontal one of negative 45 cosine 70 plus a vertical one of negative 45 sine 70, which looks like that. So am I allowed to substitute these two for my downward vector, my 45-degree downward one, and these two for my upward 250-pound vector?
Are
You added them all together.
Yeah, just one big addition problem now.
You underlined the wrong two, but it's fine.
Chris, this is why we keep you around. Thank you.
I just wanted to be.
All right, no, be sure, yes, thank you for catching that. Also, my 5 looks like crap. Let me fix that. Okay, so you guys are good that these two vectors mean the same thing as this hypotenuse, and these two vectors mean the same thing as this hypotenuse, right? Okay.
Yeah.
Remember back in Algebra 1 you learned about a little something called like terms?
Maybe.
You can add x's to x's, and you can add x squared to x squared, you can add y's to y's.
Yep.
But you can't add x's to y's, you can't add x cubed to x squared. Okay,
You can't add cosine.
the horizontals are like terms, they're in green. The verticals are in red, they're also like terms. You can add all the horizontals, you can add the verticals, and they make sense. The one-dimensional stuff makes sense. If I push with negative 10 pounds, and someone else pushes with positive 10 pounds, what's 10 plus negative 10?
0.
0, yeah, nothing's going to happen to that object. One-dimensional, the stuff makes great intuitive sense, and everything you learned in arithmetic is still true. And now we've taken this two-dimensional problem and broken it down to two one-dimensional problems, a horizontal dimension and a vertical dimension. So my final vector in vector notation is going to be horizontally 250 cosine 25 plus minus 45 cosine 70, comma, because that's my vertical component. And then my horizontal component is going to be 250 sine 25 minus 45 sine 70. And that's going to be how I would add those vectors. So it's really a couple problems in one. First, it's a can you find the horizontal and vertical components of each vector problem? And then you add them. And does this drawing help you guys see which ones you line up?
Yeah.
A little bit, okay? Hopefully that will help Andrew and Emily as well. Now, unfortunately, does this book want your answer to be in the form of a vertical and horizontal component? No, they want a magnitude and a direction. All right? Darn them. Let's see. That's right. I think I have, oh, this is a picture actually takes in a bunch of the next board. Okay, I don't have to erase this yet. All right, this is where one of you guys pulls out your calculator. And carefully, so that we don't spend too much time arguing about who punched in correctly, I'm going to get my calculator and do it as well. We could just put it into the calculator like this, but once again, this is a new vertical and a new horizontal component. So the magnitude of my resultant vector, absolute value signs for magnitude, R is a resultant, is going to be the square root of my horizontal component. I'm going to do it like this first. 215 cosine 25 minus 45 cosine 70 squared plus 250 sine 25 minus 45 sine 70 squared. And my direction is going to be the inverse tangent of the y over the x, the vertical component over horizontal. Jack's got numbers, but hang on one sec.
I also got numbers.
All right, I want to see if you guys agree. Jack, what are your numbers? What's your magnitude, your final one?
I have a question. Instead of just leaving it really wide, couldn't you just solve what you can just multiply 250 cosine 25 minus 45 cosine 70 and just put that number into the
You absolutely can. Why do I sometimes not do that?
to notes
Partly, but even we talked about this before.
or precise.
It will carry out more significant figures. Your calculator will keep track of more digits if you put it in this way than if you round and put it in.
Yeah.
So that's one part. Another part is, remember what I told you guys, if you want me to double look over your shoulder and see if you made a mistake somewhere?
Right.
As soon as you put in decimals, I really struggle with that. So, but if you like put this into your calculator and call this up, maybe I can see what you did wrong. Maybe not.
Okay, so
I think we're good.
Okay.
But actually, yeah, go ahead and take a look at it. Duck under carefully, Ethan, and take a look and see if you can turn it a little bit. Awesome. Okay.
wait.
I love wide angle lenses. Yes.
Which one? So which one back to which direction?
Okay. The magnitude is the one that looks like the Pythagorean theorem, although it's hard to see here that it looks like the Pythagorean theorem. The direction is going to be theta. Theta is sort of like x for angles. It's got the inverse tangent. This will give you an angle. The magnitude is this big mess up here. And who's ready to tell me what each one is?
I have the mag.
What'd you get for the magnitude, Chris?
I don't have the magnitude.
220.5.
220.5. First question, pounds. This was pounds, right? First question, is this a reasonable number? Let's take a look.
Oh, God.
Smooth. I'm glad that was on film. Okay. Here was a 250-pound vector, and we said that our diagonal of our parallelogram looked like it got shrunk a little bit. So is 220.5 in the right ballpark? Is it a reasonable? Yeah. Remember in physics we talked about order of magnitude? It's definitely the right order of magnitude. So I wouldn't automatically, like if you'd gotten 500, I'd say, oh, okay, there's a mistake. If you'd gotten 12, I'd say, okay, there's a mistake. But I was looking for a number a little less than 250. Yes, Jack?
I got 16.947.
Please tell me that's for the direction.
No.
You wait for the magnitude?
Yes.
We'll talk later. I know for a fact it's not 16. What do you mean? If this is 250 on my parallelogram, that vector cannot shrink to 16.
This is why I like doing it in class.
We'll talk. All right, we'll talk later. I'm going to stick with Chris's for now. Anyone get this as well?
No, actually,
yeah.
I got something more. Okay.
How much more?
I got.
Well, I got 300 pounds.
How do you know that can't be right?
Because it's over 250.
Because there were two.
Yeah, it's not going to get bigger with the other vector pulling in the other direction.
No.
All right, so you know that was not going to be. How much less did you get?
Oh no.
Okay, that's good. All right, good. Okay, now, Jack, the number you gave sounds like a reasonable estimate for the direction. So inverse tangent y over x, Pythagorean theorem for the resultant. But okay, what?
Yeah.
Who's got a direction for me?
I got two.
Oh,
I got the 220 thing.
Awesome.
16.7.
Jack, you sure you didn't just mix up the magnitude and direction? Okay, so
Yeah, I think you mixed up the thing.
it's okay. Does 16.7 degrees seem reasonable?
Yeah.
I think so. Remember, your calculator can only give inverse tangents first and fourth. Your calculator can give you any answers for inverse tangents from 90 degrees down to negative 90. We'll get why that's true a little later. So because of that, your calculator does not know the difference between 16.7 degrees in quadrant 1 and the opposite of that, 196.7 degrees in quadrant 3. Add 180 to that. Is there any chance, though, that a 250-pound vector pulling northeast and a 45-pound vector trying to pull it down is going to wind up pulling this object down into quadrant 3? No. This is the 16.7 is definitely the right answer.
Yeah.
Okay?
So that would be 196.7.
Exactly. And 190, but there's no way something pulls 250 and the only thing resisting it is 45 pounds this way that it goes in the opposite direction of the 250. Okay.
How can you tell when to check?
I always draw the parallelogram just for reference. Not because I think it'll give me an exact angle or because it'll give me a exact magnitude, but it'll give me, at least I'll know what quadrant I'm looking at.
Okay.
You know, so I try to do a good job just sketching the parallelogram, not doing it exactly. And that should do it. All right, any questions on any of these steps? I'm hoping Emily and Andrew aren't here. I didn't review at all where this comes from or where this comes from, so you have to already know how to find the magnitude and direction of a vector for this to be of any use. Yes?
So how do you make sure you don't make a mistake when plugging in the magnitude?
You're less likely to make a mistake if you switch to decimals earlier. That is true, and carefully copy the decimals in. You just have to be really careful. Key to success in honors pre-calculus and above is learning to love the details. Just learn to love looking at this and making sure every number is right, making sure you went cosine, cosine, sine, sine.
You see that all the time.
I know. Love the details. You gotta love the details. If you love the details, the stuff will start making sense faster than if you hate the details.
So like Chris.
Chris does love the details.
I just noticed.
Chris is a
it,
detail man.
It is. All right, let's go on to the next one, and we'll do the next one a little bit faster, but I really wanted to go over like how vector addition works and how you can think of it horizontal and vertical vectors as being like terms and break it down. So let's see.
Are we do another one?
Yeah. Take a look at number 20. Because 20 has 3 forces. Pardon, please? It should be. Let me check.
It is.
Yeah, we'll keep, yes, we'll record some more. Okay, so we're still on page 517, and here's what number 20 says. Number 20 describes 3 forces. And I'm just going to translate it real quick, okay? And the 3 forces have magnitudes, they say, of 70 pounds, 40 pounds, and 60 pounds. And they give some crazy angles here. So up here, this is going to be kind of like a unit circle where I'll keep track of my angles. 70 pounds goes with the 330 degrees. How does that look for about 330?
Actually pretty accurate.
Like perfect.
Pretty accurate.
It's a little less than 30, but I'll take it. And that's supposed to be 70 pounds. And then there's see if different colors make it stand out anymore.
Oh yeah, yeah.
The middle one, 40 pounds, is at 45 degrees. So 40 pounds, I'm going to try and make it a little more than half. And 45, I'm going to try and go up with a slope of 1. So there's 45 pounds, and there's my 45-degree angle. How's that look?
Good.
Is that a positive x-axis?
I'm only given the magnitudes and the angles, Ethan, and I'm going from 0 degrees being the positive x-axis.
Is that 45 pounds or 45 degrees?
That's a good point. Let me see if I'm misreading this. All right, thank you. That's 40 pounds. Excellent. You gave me numbers too similar, and love the details, Jordan. Awesome. Love it when you guys catch that. All right. And lastly, okay, 60 pounds at 135 degrees. 135 should be perpendicular to the 45, and 60 should be a little bit bigger than 40 and a little bit less than 70. So I'm not going to pull out a ruler and protractor and double check your drawings on your work, but I do expect things like 60 is less than 70 and more than 40. You guys can handle that level of precision, right? Okay, I'm not going to draw the parallelogram. It's kind of harder with, I don't want to do this with 3 vectors. I have to do it with 2 and then I have to do that again with the other one. I don't think I really need to, because in general, which way do you think this is going?
What's the directional order?
For which one?
So what's the order of the angles?
Oh, the angles they get? Hang on. Okay, Jack had a good question. I'm not going to draw the circles, Jack, because I think that'll make it messy. So that's 330 degrees. This was 135 degrees.
Oh, there you go. That helps a lot, actually.
And this is 45 degrees.
So you shouldn't try to break it up in your own triangles, try to put them all.
I'll give you a minute. We're just sketching the situation.
I think one thing I did wrong is that I always put the vectors going this way.
Yeah, don't do that.
All right.
Okay, all right, you gotta just, sometimes I'll ask you to sketch the actual situation.
It's pulling more to the right. A little bit
It's
down.
to the right.
A little.
I'm
Yeah.
seeing up and to the right.
Yeah.
Yeah, it's gonna go that way.
Yeah.
These are gonna mostly pull against each other.
So then, wouldn't that be like a really weak pull up here? Like, wouldn't that be like
Well,
a-
these two should result in a fairly weak pull up that way. Maybe a little more down here because the 70 is bigger than the 60. And then this 40 looks to me like it's going to wind up going mostly in the direction that the other two would pull.
I'm just trying to think of this as like a string and 2 people pulling. That's the way.
That's a great way to picture it. Or like if Yeah, if two people are pulling on that string, almost like a tug of war, but they're going slightly to one side, and then a third person is
Has a
in
third
that
string.
direction.
Yeah.
Yeah, it's going to go that way. But there's a lot of, if this is an effort to pull something, there's a lot of wasted effort over here. They should all three just be working more in tandem. Okay, but it's definitely going that way. So anything we get in quadrant 1. Now,
It's right.
yeah,
Oh, that's the estimate of what's it called?
order of magnitude.
Order of magnitude. That's a.
Order of magnitude estimate. It's going to be somewhere between 40 and more than 40 pounds going that way. That's my order of magnitude estimation. Now, if you've got a good visualization from the first thing that we did, we can start taking a couple shortcuts. Plus, they gave us standard angles, which is nice. These are all from 0 degrees. I like this. Because on the last one, I kept careful track of the positives and negatives. I'm not going to do that this time. This 41, I know it's going to be an adjacent side and an opposite side, right? And I know that I'm going to find the adjacent side with the cosine and the opposite side with the sine. So I'm going to go right to describing that as 40 cosine 45.
Which is root 2 over 2.
It is, but I'm not going to pull that. Well, actually, no, we could. Hang on a second. Hold that thought a minute, Jack. I'm going to use that. 40 cosine 45, comma, 40 sine 45. Because you guys now know, in your imaginations, you're breaking this vector up into a multicolored set of pieces with a horizontal part and a vertical part. But you know it's going to be, the horizontal part's going to come from the cosine, the vertical part's going to come from the sine.
Having the right triangle.
Just the red. It's just the red vector. So I'm kind of doing
So how many triangles do we have to make? 3, right?
three vectors.
Are you trying
So
that?
then how would you take?
Go ahead, Jordan. Finish yours then.
How would you like write that as something like that?
Oh, we're not there yet.
Okay.
After we add all our individual components, then we go there.
Okay.
All right. Now, so Ethan, your question.
Are you trying that to scale?
No, not at all. I kind of meant to, but wow, I did a horrible
Sorry,
job.
No, that's right.
My schedule's different, but it might
Yeah.
be the same.
It's not bad, but
It
okay.
needs to be farther down.
Now the green vector, if I was going to break this down and draw the triangle and keep track of the directions, I'd find the reference angle of 45 degrees. I would know that the horizontal component would be negative because it's to the right, and the vertical component would be positive because it's up. But if you're confident with that mental image, we can jump right to 60 cosine 135, comma, 60 sine 135.
Can we do the other way? I was not comfortable.
Let me do this way with this time, okay? We'll get back to that. This is the exact same thing as doing that with my length of 60, okay? And I know, Jordan, that this is going to have a horizontal length of negative 60 cosine 45, right?
Wait, 60. What is 60?
60 is the length of the hypotenuse
Oh,
of
the
this
length.
vector.
Oh, snap.
It's okay.
I'm thinking about like the angle. Like I'm like 60.
Gotcha. And then 135 degrees creates a 45-degree reference angle in quadrant 2, right? Okay? So, and then I would make this, oh, this is going to the left, so that's negative 60 cosine 45.
Yeah.
And then I'd look at the vertical and I'd say, oh, that's going up, so this is positive 60 sine 45. If you want to just put in 135, your calculator knows that 135 is in quadrant 2 and any cosines are negative.
Oh, really?
Yeah, so it'll do that for you.
Oh.
If you know the standard angle. So you can jump right to here. I mean, I've done this this way because I insist you would also know what's going
Now I'm
on.
comfortable.
All right, I thought you might be. So we can jump right to that, and it's there's the positives and negatives.
Check.
Okay, and then my first vector was marched in. So, hey, we're recording. So, okay, done. All right, so this was going to be 70 cosine. I can just go right to 330.
Because you're comfortable with the angle.
I am totally comfortable with this. It's kind of funny that I mean, there are good reasons for it that we'll get to later, but
It's funny how it knows when
it knows the unit circle.
sometimes and
Forwards?
and doesn't know things like that.
There's a good reason why I'll tell you later. When we get to inverse trigonometric functions, I will explain to you guys why your calculator knows the unit circle forwards really well, but it doesn't know it backwards very well at all. There's actually a good reason for that we'll talk about. Okay, so now if I wanted to draw this, and if I wanted to, I could say, okay, that's a 30-degree reference angle, and obviously the horizontal is negative 70 cosine 30, and by negative I mean positive, sorry about that, and the vertical is negative 70 sine 30. Did I get my positive and negative right there?
Yeah.
But see, if you don't want to make that mistake and you know the standard angle, just put cosine 330, sine 330. Your calculator will take care of the positives and negatives. Okay? Now, Jack, there is a limit to how much I am willing to type into the calculator. Okay? So I would say for the resultant vector, for what's actually going on, add your horizontal like terms, add your vertical like terms. I would put this in the calculator as one long string.
And then
Get the decimal. Yeah, I'm not typing all of this.
You didn't write a negative 70.
No, I didn't. Why didn't I?
It knows what.
Because I put 330 in the calculator, we'll make that negative off. Well caught. Good job. Good job. Love these details.
I thought you didn't catch any detail. I thought just the detail.
No worries. Okay, so take out your calculators, start going. What's 40 cosine 45 plus 60 cosine 135 plus 70 cosine 330? Bothers me that I'm inconsistent.
Thing won't come in handy now, will it?
We could. This would be a horrible no calculator problem, but it would be a fair one because these are all sines and cosines you should know. Yes.
Oh,
Why do we have to draw those triangles?
You don't actually, but I'm trying to make sure you understand visually what's going on as well.
Okay, because I can just get it.
That's fine.
Yeah.
Yeah.
Well, yeah,
would
but
it be like 70 cosine 330 then? Would it still be positive for like the one beside it?
Yeah, it actually wouldn't make a difference whether you put 330 or 30 in because they're both positive.
Or like negative sign. So,
I got 46.
you don't like subtract, like they're all positive for that?
No. Your calculator knows that the sine of 330,
Oh, okay.
and you know how the sine of 30 degrees is 1/2?
Yeah.
Well, your calculator, if you just put sine 330 in your calculator, it'll give you negative 0.5.
Oh.
It knows.
Oh, okay.
It knows the unit circle forwards. Doesn't know it backwards very well. We'll talk about why later.
Well, should I put the entire decimal or should I just?
It's up to you. You can store it to memory. I'm just gonna go like, Ike said 10.1.
No, it's 46.
I got 46.4.
It's 46.4.
I'm gonna go with you two.
Yeah.
All right. Ike, you okay with that?
Yeah.
All right.
I got 652.7.
Yeah, Jack, you and I are gonna talk about the calculator later. Okay? And now for 40 sine 45, 60 sine 135, 70 sine 330.
I got 35.7.
If you think about it, this is actually it's really tedious, but it's really fair.
I agree. I agree with that completely. Okay, first off, do these numbers make sense? Quick order of magnitude estimation.
Yes.
We said we thought it would go up to the northeast, it'd be in quadrant 1, positive, positive, we're in quadrant 1. And these numbers are pretty close to the 40, and we said the 60 and 70 would mostly cancel each other out because they kind of look like they're in a tug of war, right? Okay, so I'm comfortable with this. I don't see any reason now to assume we did anything wrong. Doesn't mean we're right, but I didn't get like, Jack, you get 600 and something? That seems unlikely. Okay, because these two are mostly canceling. A 40-pound pull this way shouldn't
My
create.
calculator maybe.
It's out.
Radians maybe? Check.
It is in degree.
Okay, we'll figure it out later. Now, let me review this step a little bit because,
Is this everyone messed up? Or?
yeah, the magnitude, the actual answer, absolute value sign of means magnitude, R means resultant vector. It's a variation on the Pythagorean theorem, which is the distance formula is what it most looks like. So it's another variation on that.
Average.
The distance formula is just the Pythagorean theorem. It's the horizontal component squared plus the vertical component squared, all under a radical sign. Just like your distance formula is x2 minus x1 squared, y2 minus y1 squared, horizontal and vertical, same thing.
I'm gonna take a trick for that.
You want an answer on that?
Okay. So this should be the square root of, if that's correct, 46.4 squared plus 35.7 squared. And what are you getting?
15.6.
That seems reasonable to me.
I put all the digits in there, so I counted it right.
It's probably different than what you'll get if you just plug this in then.
Yeah.
Okay, good. If I were feeling really like I had a lot of time, I would, if I really needed this to be ridiculously precise, I would put in 40 cosine 45 plus 60 cosine 135 plus 70 cosine 330 squared plus, that would be kind of insane though, for this level. We're not actually trying to program a GPS. Okay, does this seem reasonable? I said it looked like the 40 pounds. These would mostly cancel out, but they would pull a little bit in that same direction, right? So does that 58.6, that's like just the 40-pound pull got a little bit of help from these two. Does that sound reasonable?
Yeah.
All right, now direction. To find one of two possible guesses from the direction, since your calculator is not as smart with inverse as it is with straightforward trigonometry.
Maybe 35 over to 40.
Yes. Quick, before anyone touches a calculator, tell me how I know this is going to be a little bit less than 45 degrees.
Because you're
Because
dividing
40 is
35 by
smaller.
40, by
What?
40, 30 something by 40 something.
Close. And what is the tangent at 45 degrees?
Oh,
1. It's 1.
damn it.
Okay, so at 45 degrees, you have a tangent of 1. So if you're putting the smaller number, okay, it's vertical over horizontal, right? If you're putting the smaller number on top of the larger number, your fraction is less than 1, right? Your angle will be less than 45 degrees. If we were putting the larger number on top of the smaller number, tangent would be greater than 1, we'd be expecting an angle a little bit more than 45 degrees. And we've got the 70-pound pull going down, so I would expect that to tilt this 45 degrees downward a little bit, because it's the bigger pull. So we find the inverse tangent.
37.5.
6.
0.6, you're right.
35.7 over 46.4.
37.6.
37.6, less than 45 degrees.
Right, bang.
Bit of a lower angle than I thought it would be, but I'm horrible at estimating inverse tangents. So
I imagine it's a pretty hard thing to do.
I really don't know who can. Basically, if it's going to be close to 1, then I know it's going to be close to 45, and I can figure out bigger or less, but that's really where it ends. Yeah, that's as much as I can do with it.
I can say numbers and.
But do you see how you can use like your unit circle knowledge to double check what you're doing? Yes, sir.
How do people get the arc cosines of things without calculators?
We'll talk this much about that in about 3 or 4 weeks when we get to what are trigonometric identities and a few other things. We'll start talking about that.
Did they just have? Were they smarter than we are?
Well, one argument would be no, because they didn't invent the calculators that could do it.
Algebraically they are.
But algebraically, yes, they had to be. But fewer people can do it as well.
So,
All right, that's all class. We won't spend on two of the examples. We'll go over more tomorrow, but I really want to make this clear, and now you guys have this as a resource.
Ball and can we talk now?
Not yet.
Flag!